So we will continue our discussion on search methods. First we look at the nature of the objective function. There are some important definitions that we will have to flesh out. For example, what is a monotonic function, what is a unimodal function, what is the concept of a global minimum, what is the concept of a local minimum, and all that, and these are best understood in relation to a single variable problem. Then once you can understand with relation to single variable problem, you can understand with respect to other multivariable problems also, because optimality criteria for multivariable problems we have already established, right, Hessian and all that. So we look at some basic properties, nature of the objective function, and then we will start off with search methods. A very crude search method was already discussed yesterday, namely the exhaustive search method, where if you have n observations you can reduce it by how many? Original interval is b minus a, so you are able to reduce it to b minus a divided by n by 2 or something, right, something like 2b minus a divided by n or something like that. Now we will see algorithms which are much more powerful than this, which can rapidly reduce the interval of uncertainty, right. So the nature of the objective function, whatever discussion we are going to have is basically with respect to a single variable problem, and we can extend it to multivariable problems very easily. So a function f of x is said to be monotonic Can you complete the definition? A function f of x is said to be monotonic. No, you start with some x1 x2. You start with some x1 x2. Function f of x is said to be monotonic if for any x1 x2 a function f of x is said to be monotonic if for any x1 x2 with x1 less than or equal to x2 f of x1 what is this, monotonically increasing. Monotonically decreasing. Okay. Okay. I have graphed 3 possible situations. Yeah.
There should be equality. Strictly, otherwise it would be strictly.
There will be equality. Okay. Okay. Let us complete this. So this is monotonically this is also monotonically monotonically increasing. But what is the problem with this, with the function I have sketched at the bottom? It is discontinuous. Okay, what happened? What is continuous? Huh? How is it continuous? The same value of x gives two values of y. It depends on what they have taught you as continuous. For me, if there is a value of x, there should be unique value of y. Any other definition I will not accept. The greatest of mathematics process can tell me. If there should be unique values, isn't it? Differentiable and other things will vary later. I am coming to that, whether it is differentiable or okay. So this is with regard to a monotonicity. What is the next logical step? What is a unimodal function? Okay, unimodal function. If the problem is I have drawn lines, you just replace it by points. If you feel that your problem arises because I have joined it, you can keep it like this. If that is your problem, okay, remove the line. According to me, if I give one x, I cannot get two values of y. As an engineer, it will trouble me too much. Whether the size of a nut or bolt should be 2 millimeter or 20 millimeter, it will really, I cannot sleep. Mathematically, so many things are possible, but basically we are engineers, right? So the way we look at things is different. All right, okay. Unimodal function. A monotonic function is said to be unimodal. Can you complete the definition? A monotonic function f of x is said to be unimodal. Okay, a function is unimodal in a less than equal to x less than equal to b. A function f of x is unimodal in a less than equal to x b if, that is if and only if, it is monotonic on either side of x plus, where x plus is the single optimal point. Okay, it can be beautifully depicted graphically. So y of x, suppose you have a parabola like this, about the optimal point it is monotonically increasing to the right side of, for all x greater than equal to x plus, it is monotonically increasing. okay. It is a, therefore this is a unimodal function. Okay. How we determine the optimal point is something different, we already seen, I mean you are going to see also, right. Once you have an optimal point, it is increasing on one side of the optimal point and it is decreasing on the other side of the optimal point. Now we will come to the function which all of you worry about, y equal to mod x, okay. Students seem to be obsessed with y equal to mod x, huh? Alright. What is the optimum for this? Minimum, if you want to minimize 0. So this is the x plus, okay. Is it a unimodal function? Sure it is unimodal. However, so it is continuous because there is, whether you approach from the left hand side or you approach from the right hand side, at x equal to 0 y equal to 0, therefore it is a continuous function, there is no discontinuity. That is, when you are coming from one side of x, if it gives one value of y, if you are coming from the other side of x, it gives another value of y, then there is a discontinuity. This function exhibits no such behavior. However, if you try to plot dy by dx, how does dy by dx look like? Correct. What is his value? 1. Dy by dx is discontinuous at x equal to 0. Because dy by dx is discontinuous at x equal to 0, y equal to mod x is not differentiable at x equal to 0. Okay. So many teachers have told you from JE, you consider it is a big thing, it is a trap, you can find out whether somebody knows maths, what is y is equal to, whether it is continuous differentiable. Okay. So we will put the lid on this, continuous but not differentiable, but still you can find an optimum. So there is no need some function has to be always differentiable to get the optimum. This is a very nice example, okay, continuous but not differentiable. Okay. So dy by dx discontinuous at okay. So we are trying to seek a solution to the optimization problem for a single variable problem if whenever it satisfies this property of being a unimodal function. If it is multimodal, you have to divide it into subintervals and try to seek the unimodal optimum at that particular point, okay, or in the particular interval, otherwise we are in trouble. Are you getting the point? You have several local maxima and minima, and you have to subdivide the interval and seek the individual local minimum or maximum. Now we will come to the definition of global. What is global and local minimum? A function f of x is f of x on a domain, okay, let us say on a domain R. A function f of x on a domain R is said to attain its global optimum. Can you give me the condition? You can say at a point x plus plus, at a point x plus plus is contained within the domain R if means if and only if f of x plus plus, very good, f of x plus plus is less than equal to f of x for all x belonging to R. There will be no point x at which y can take a value which is lower than the value which is taken by y at the point x double plus, okay. This is the, let us say it is a global minimum, I should say, right. A function f of x is said to, a function of f of x on a domain R is said to attain a local minimum if x at a point x plus is contained within R, or x plus lies within the domain R, if and only if. Can you complete? Function f of x on a domain R is set to have local minimum, I should say, double if is if and only if, right. Yeah, this is tricky.
X plus.
Very good. So, if f of x plus is less than equal to f of x for all x, I will make it non mathematical here, for all x which lie within a reasonable distance from x plus. What is that reasonable, we will decide, okay, within a, I can make it threateningly formal by calling that reasonable distance at epsilon, epsilon plus gamma, whatever. It is not central to our this thing, but the conceptually you would understand. So, for all x which lie, within okay. So, if you located local optimum, if you perturb the value of x around that, you will not get a value of f which is better than this. However, it is not global, because if you go far away from this x plus, there could be other positions of x where the f of x could be significantly lower than this, okay. So, this is the difference between global optimum and local optimum, or global minimum and local minimum. Now, one, 2, 3, 4, 5, 6, 7, all are among the 7, 6 are local, okay. So, x1, so is f of x versus x, This is the lowest, right? Is everybody agreeing to this? These are all conceptual frameworks which are very important. There are 3 important points which I want you to remember. If required, we will write them on the board. Point number 1, for a unimodal function, the local minimum and the global minimum coincide. For a unimodal function, if you want you can write it down in telegraphic language. For a unimodal function, the local minimum and the global minimum coincide, there is no doubt, right. For unimodal function, the global minimum and the local minimum coincide. Point number 2, for multimodal functions several local minima exist. For multimodal functions several local minima exist, we saw that on the board. For multimodal functions several local minima exist. We need to evaluate y at all these local optima. We need to evaluate y at all these local optima and select the lowest one for getting the global minimum. You write it in your own words. So, we need to evaluate y at all the local optima and select which of them gives the lowest value of y, that is the global minimum. So, it is a lot more difficult, it is a lot harder to solve a multimodal objective function problem. Okay. So, algorithms have been specifically developed which can handle this, which can handle multimodal objective functions and which can finally or eventually give you the global minimum. The problem with some Lagrange multiplier, any calculus based technique, is if you start from here, it will say that this is the answer, then if you go this side, whatever test you do, it will aver that this is the answer, but it does not know that it is in error because this is the correct answer. That is why people have come up with simulated annealing, genetic algorithms and all that. In genetic algorithm, for example, a quick half a minute course on genetic algorithm, I will come to it towards the end. A quick half a minute course on genetic algorithms, basically we will look at the complete solution space, we will look at this complete solution space, and at any point of time we will look at 5 or 6 solutions, and then these 5 or 6 solutions will be replaced, just like parents reproduce and then it results in new offsprings and so on. New generations we will see, we look at the quality of the solution, that means we are looking at f of x. By repeatedly searching in the complete domain, we are ensuring that we do not miss out on these global properties. There are several ways of, so the basic problem with calculus based techniques is they are extremely fast because derivatives, they force the derivatives quickly to 0, they are fast, they can be highly inaccurate, they will quickly converge to the wrong answer, that means a local minimum, that is called premature convergence. Okay. So, we will talk about it a little later. So, the first point was a unimodal function, the local minimum is the same as the global minimum. Second, for a multimodal objective function, you have got to evaluate all the local minimum and then pick and choose the best. Third, we can modify this definition for a maximization problem. The definition for global and local minimum can be modified for a maximization problem, alright. So, now we know what is the nature of the objective function, what are the properties it has to satisfy, how to get the optimality criteria for using calculus also we have seen, how to establish, how to look at second order necessary and sufficient conditions, all that we have seen. Now we will go to, formally we will go to search methods. Now before going into a region elimination method, let us look at a broad overview of search methods. We looked at one category where we divided the whole interval into 7 or 8 divisions, maybe yesterday's 6 divisions, and we evaluated the function at 7 point. We removed certain portions of the interval because they do not lead to the minimum. Okay. That is called as a region elimination method. You eliminate a portion of the interval each time you do some function evaluation. Are you getting the point? That is, sometimes you halve the interval, you quarter the interval, you halve the interval and make the interval 2/3 whatever. You are cutting a portion of the original interval of uncertainty by using your procedure, by using your logic or algorithm or whatever. But that is not the only conceptual way of solving a optimization problem with the search method. There is another possibility. For example, so the 2 variable optimization problem, I am looking at a minimum. Okay, this fellow is the minimum. For example, I am drawing contours. So y is increasing. Iso contour lines, iso cost lines, iso cost lines or whatever. Okay. Now it is possible for me to come out with a rectangular grid like this. I will start from somewhere, point P, okay, east, west, north, south, southeast, southwest, northwest, northeast. For a 2-dimensional problem, a 2-dimensional means y is a function of x1, x2. I will have a rectangular grid. To make matter simple, let us say we assume a uniform grid for both x and y, that is del x1 equal to del x2. Now I look at the 8 neighbors, right, correct, 8 neighbors, no? Yeah, we look at the 8 neighbors and see and evaluate the value of y with respect to this. So totally I am doing 9 functional evaluations. Depending on where it is lowest, it will go either in this direction or this direction. Anyway, now I know that it has to go in this direction. This is the direction in which it will go. Now this fellow will be the center. I will get 9 points around this. Okay. Conceptually, this is an altogether different story compared to the elimination of the interval by using the exhaustive search, right. Here we are systematically climbing towards the top. I mean, if this can be considered as a summit or the hill top, we are systematically proceeding towards the top of the hill. So this is called a hill climbing technique. Okay. Conceptually it is much different from cutting. I am not cutting the interval, I am not saying that this x1 is not good, this x2 is not good, I am not doing anything like that. Okay. So this is called a hill climbing technique. I start with one guess and I am trying to move that guess till the value of y keeps decreasing. Okay. So this is a hill climbing technique. So conceptually you have 2 different approaches. You can have an elimination method or you can have a hill climbing method, right. So let us write down the framework for solving optimization problems using search techniques. By the way, this is called a lattice method. If you do not have time and money to invest in a sophisticated optimization algorithm, you want a quick solution, instead of exhaustive search you can go for that. Okay. No calculus, nothing, just keep on getting y, right. If getting y is so difficult, you can use a neural network and you can get the solution for 10 values of x1, 10 values of x2, set up a neural network which when supplied with x1 and x2 will automatically give the value of y. Okay, that is a neural network based lattice method for solving a n dimensional optimization problem. There is already a paper. Okay, so overview of. So, but if you want to write a paper, what you have to do is first you have to prove it for what is called a Himmelblue function or a banana function. Banana function, Himmelblue function is something which has 3 or 4 local optima, but there is only one. X1 squared plus x2, x1 squared plus x2 minus 7 whole square plus x2 squared plus x1 minus 11 whole square, it is something like that. People have worked on that. You prove that your algorithm works, it leads to some solution where y is equal to 0. So I have established my algorithm for the standard Himmel-Blue function. Now I am proceeding to the fluid mechanics, thermal power, energy system, heat transfer problem. It works. This is the approach. Send your paper and see how far it flies. Okay. So overview of search methods. So the framework, basically we have elimination, hill climbing, under this single multivariable, constrained, unconstrained. I don't want to put constrained and unconstrained here, though it is possible. Already it is single variable. Why try to constrain it too much? Okay. So this is unconstrained, but don't ever imagine that in none of these techniques we will use calculus. We will use calculus, but we will not use calculus to make the function stationary. We may use calculus to find out the best direction in which we have to go. There is a difference. I am still searching. I am starting with a guess point. What is the best movement from that position 1 to position 2? That I will take the help of calculus, but I am not using calculus to make the whole function stationary, like what we use in the Lagrange multiplier method. There is a difference. Are you able to get this? Okay. Likewise, elimination also you have single multivariable and then you have two, constrained, unconstrained. Okay. Let us see in the coming classes how many of these we will be able to discuss. For example, the toughest will be a constrained multivariable optimization problem, and suppose are we able to discuss something in the class, a hill climbing technique for a constrained multivariable problem, or an elimination technique for a constrained multivariable problem. Okay. How much of this we will be able to cover depends on the time we have. All right. Now this gives you overview of the search method. Now I taught you some exhaustive search, right? It comes under which category? We already learned one, single variable, unconstrained. Was it unconstrained? No, it was constrained, but you converted it to unconstrained. Oh, single variable, unconstrained, elimination. So we already. So I don't have to teach you anything else. No, I will teach you something more than that. But we already seen this. Now we will see how many of these we are able to circle. All right. Okay. Now I need the full board. So elimination method. So what is the funda behind this? What is the basic funda? So we will see that. Drawing the same function, okay, f of x okay. AB we are seeking a minimum in the interval AB, okay. All right. This looks like an additional line, we'll remove him, huh. Yeah, are you able to get the story? There is an interval AB, I am trying to seek a minimum in this interval, f of x is unimodal, it is monotonic at I know that it will become unimodal, that is once it is unimodal, if I seek an optimum on one side of the optimum it will be monotonically increasing, the other side of the optimum it will be monotonically decreasing. The challenge is to get the optimum without taking recourse to calculus by using a search technique and with a final interval of uncertainty. Now f of x1 is less than equal to f of x2, case A, agreed, sorry, greater than. B, f of x1 less than f of x. This is f of x1, hopefully I have drawn it all right, f of x1, correct. I am seeking a minimum. So what is the story now? When we are seeking a minimum, if f of x1 is greater than f of x2, from this based on a simple, this is called a simple 2-point test, that is 2-point test means you take 2 points and evaluate the value of y at these 2 points, y at x1, y at x2, and look at the nature of y, whether y of x1 is greater than, less than or equal to y of x2, very simple. So what is the conclusion? Logically you can draw f of x1 is greater than f of x2. No, I am talking about the elimination method. Region to the left of x1 can be, very good, region we will write, region to the left of
x1.
x1 left of x1.
I have written x1, no? Yeah, where did you write x1?
You cannot write x2.
Left of?
No.
No, it can go like this, no. How do you know that it is now? How do you know you already reached the optimum? Who told you? I can only say that since it is decreasing, it cannot be left of x1. Be very careful, because it is not such a fine division. Between x1 and x2, so much story can take place. It is not decreasing. I am saying with I don't know whether it is decreasing or not. I am evaluating spot evaluation. I'm not drawing the function. I can evaluate at 2 points. Decreasing means f of x1 is greater than f of x2. That is the information I have. With that you cannot conclude that everything to the right of this thing can be, everything to the left of x2 can be eliminated. That is not correct. This is very simple logic. I don't know why you are not able to get it.
How can we predict the left of
I am already telling you it is a unimodal function. Wherever you go, the logic will correct. It is a unimodal function. We are looking at a unimodal function. I have taken sufficient care to ensure that I am looking only at that interval in which it is unimodal. Now everybody will get a doubt, sir, we can take to the left of x2 also we can eliminate, but that is not correct. Okay. So it could have been like this also, right? It could have been like this. You still don't know, right? You don't have the luxury of evaluating the value of x at you know at every point. You now have only x1 and x2. All right. So region to the left of x1 can be eliminated. Here region to the right of x2 can be eliminated. Here left of x1 and right of x2 can both be eliminated. Okay. For a unimodal function, f of x in the closed interval a less than or equal to x is less than or equal to b, for the minimum does not lie in ax1. Good. Minimum does not lie in ax1. Minimum does not lie in x2b. Very good. Minimum lies in if f of x1 equal to f of x2. Correct. If but this is very rare in practice. When you are doing search method, you will do 1.99 x equal to 0.1991, other maybe 0.1990, then f of x1 and x2 numerically will never be equal, but it is a mathematical possibility, so I discussed. When you are actually doing computation, it will never happen. There will be always a small difference between x1 and x2 because round off errors, this thing, and you are getting the point. So we can use this 2-point rule and come out with various algorithms. Okay, we can come out with various algorithms. I will just give you a sneak peek into a very powerful algorithm called the dichotomous search. Okay, we will work out a problem in the next class, but on the basis of this elimination method, we will start off with the first algorithm, namely the dichotomous search. Is this clear? The logic is clear? Vikram, you have any problem?
Yes sir, it depends on your function, right? You can you defined a monotonic function behavior.
No, monotonic is ruled. After that, unimodal.
If it is still unimodal.
So as in it should be strictly monotonic. Then as in we can have the function we as
you can have a function like this, inverted omega.
Flat line, then and then again a flat line. So that
that we are looking at well-behaved functions. Huh? I think here something like this or okay. I think sometimes you try to specialize in finding out the exception, right, where something can go wrong, where the teacher can be caught. Yeah, that is also okay, that makes us more and more alert, right. Okay, the dichotomous search is very simple. So, if this is okay, x equal to a, x equal to b, this is I naught. Let us look at the center of this and let us take 2 points on either side. These 2 points are at a distance epsilon by 2 from the center. Okay, this is x1, this is x2. Now that epsilon can be made very small. Okay, now what is this? In terms of I naught plus epsilon by 2. I naught plus epsilon by 2. They up to this, not x1 up to x2. Be alert. I have done the homework. You want to say it's I naught minus epsilon by 2. That's a dumb answer. I naught plus epsilon by 2. Anand, got it? Huh? I naught I have written on the top. Did you go for the I test? Everything is I. I naught. Okay. Okay. So this is I naught. This is also I naught plus epsilon by 2. If I do a 2-point test on x1 and x2, how much of the interval can I eliminate with just 2 function evaluations, you tell me. So carry out the 2-point test. Forget about the case when f of x1 equal to f of x2. Either the interval to the left of x1 or the interval to the right of x2, which are both equal to I naught minus epsilon by 2, is eliminated. If epsilon is sufficiently small, that is epsilon is much smaller compared to I naught, we ditch the epsilon. Therefore, every 2 evaluations will reduce interval by leave the epsilon. Every 2 evaluations will reduce the interval by half, or every function evaluation will reduce the interval by 25%. 2 evaluations will reduce by 50%. Yeah, deliberately I say 25%, then you get confused. I am also checking whether you are awake. If you do 2 evaluations, it reduces by 50%. So it is equivalent to saying that every function evaluation will reduce the interval by 25%. But it is a 2-point test. You can't have an odd number of evaluations. Every time you should have two evaluations. So it is even number. So every 2 evaluations is reduced by 50%. It is fantastic. In 8 evaluations, it will just reduce by 16. 8 evaluations we struggled. What will it do? The exhaustive search, how much can it reduce? Okay. So the dichotomous search is indeed an extremely powerful algorithm. So in the next class we will revisit the cylindrical solar water storage heater problem and solve it using the dichotomous search. But you will be dismayed. You will be dismayed to know that there are algorithms which are more powerful than this. Okay. This is not the be all and end all of single variable search method, right. We will stop here.